Hello. In this section, in the last class, we learned how to calculate the determinant. In this class, we are going to study the application of determinants. So, determinants is pretty useful. So we have two applications here. The first one is adjoint method for the inverse matrix. So we use determinant to find the inverse matrix. So let's see. Application of the determinant. Okay, so the first one is called the adjoint method for the inverse matrix. So we are going to use determinant to find the inverse matrix. Before we use the Gauss-Jordan method, right? So let's see. The inverse matrix equals this one. Adjoint matrix of A divided by determinant of A. So I'm going to show you what's the adjoint matrix A. So ADJA, this is called the adjoint matrix, denotes the transpose. Do you still remember what is transpose? It's like an AT, right? Something like that. Transpose. Okay. The transpose of the matrix obtained by replacing each element by its cofactor. Each element in A by its cofactor. Okay, so here we need to review cofactor. Okay, cofactor. So here I can give you an example. Let's see. We just look at a 2 by 2 matrix. 1, 2, 3, 4. What is the adjoint matrix of this one? So for example, if this is A, what is the adjoint matrix? Okay, adjoint, sorry. Adjoint matrix equals to, so let's see, in the first position, this element is replaced by the cofactor for 1. Cofactor 1 should be like determinant of the matrix, delete the first row, first column, like number 4, right? But cofactor has the sign. So cofactor is negative I plus j, Cij, do you still remember? And times the Mij. Mij means the minor, means the matrix delete. I's row, j's column, cofactor. So for this one, it's negative 1 to the 2 plus 2 times 4, so it should be positive 4. Okay, adjoint. And for the number 2 cofactor, for the next position, for this number 2 cofactor should be negative 1 to the 1 plus 2 power, which is negative, and 3 is the minor. And for the number 3, cofactor should be negative 2. For the number 4, cofactor should be positive 1, right? Because I plus j is 2 plus 2, which is positive, and the minor is 1. Okay, this is the adjoint matrix. So let's take a look at this in example. I'm going to show you how to find the inverse matrix by using adjoint method. So let's see. Use the adjoint method for inverse matrix if A is given by 3 by 3 matrix. This is 3, 4, 2, 7, 5, 8. Okay, let's see. We want to use adjoint method. So first step, we can find the adjoint matrix A. Okay, so this equals what? It's kind of like it's also called the matrix of cofactors. Okay, let's find, because for 2 by 2 we can find that directly, but for here let's find cofactor vector. Okay, cofactor matrix, and then this is called cofactor matrix because we need to transpose this later. For this one, we forgot to transpose actually. This is cofactor matrix. Cofactor matrix. Adjoint, we should transpose. So should be like first row become first column, second row becomes second column, should be like that one. Okay, I'm sorry, forgot to transpose. So let's find the cofactor matrix first. So we do M means matrix, C means cofactor. So let's see. For the number 2, the cofactor should be -1 to the 1 plus 1, so should be positive, and then do this determinant. So should be 32 minus 10, 22. Right? And for the number 1, okay, number 1 here, the cofactor should be -1 times this and that. 22 minus 14 should be 8, should be -8. Let's see. Oh, 24 minus 14 should be 10 and then -10. Okay, and for the number 1, cofactor should be -1 to the 1 plus 3 power, row 1, column 3, and times 3475, right? It's like this, okay? Minus, so 15 minus 28, so here is -13, and this is this is 91 to the 4th power, which is positive, so here's -13. Let's do one more in the second row, and then we can just skip the other numbers. So let's see. For the number 3, what is the cofactor? Number 3 cofactor should be -1 to the 2 plus 1 power times the minor, means cross this row, this column, 91,158. Okay, so here should be negative times -8 minus 5, -13, so it should be +13. 13. So we skip the other calculation. I think you already got idea how to calculate the cofactor, right, of each element. So this next number cofactor should be 9, and -17, -6, 4, and the last one is 11. Okay, and after we find the cofactor matrix, we need to transpose. And when we transpose that one, is going to be our adjoint matrix. So transpose, we had this in the midterm. We change the first row into first column. And second row becomes second column. Third row becomes third column, transpose. So this is the adjoint matrix. And in the formula, what is the inverse matrix? The inverse matrix equals adjoint matrix divided by the determinant. So we need to find the determinant here. So determinant, we just do the calculation. Actually, for this determinant, that equals to, so let me write down here. determinant of this matrix, we skip the calculation. We learned this in the last class. We do row operations, create some ones, right? And use any row or any column with small zeros to expand this determinant. And this determinant is 41. So let's see what is the inverse matrix for this problem. We use, it's like a 41. 1 over 41 times adjoint matrix is like use the adjoint matrix every element divide by 41. 13 divided by 41, negative 6, 41, negative 10 divided by 41, and 9. And then you can notice this inverse matrix is pretty complicated because it has a big rational number. They have a lot of big rational numbers. If we do Gauss-Jordan method, that is impossible. Okay, so for some matrix, we may just use this method. And the calculation looks big, but if we have calculator or computer, we can calculate the inverse matrix easily by using just computer, right? I mean, I don't know, in your calculator, you may know how to calculate determinant. After you have the determinant, just divide by the determinant, we can get inverse matrix. Here, let's take a look at quick exercise problem. Let's see. This one is, let's do the 2 by 2, okay? 3, 5, 2, 7. Let's find inverse matrix by using the adjoint method. Please try this by yourself. I'm going to give you the solution here. Let's see. I like to calculate determinant first. So 21 minus 10, which is 11. Okay, next, I'm going to find the cofactor matrix. This is pretty easy, okay? So 3 cofactors should be positive 7. 7 cofactors should be 3. And for the 5 cofactors should be negative 2. For the 2 cofactors should be negative 5. And then I transpose that one, which is adjoint A, MCT, transpose. So going to be negative 2, negative 5. This is transpose. And then our determinant, our inverse matrix is just 7 over 11. 11, negative 2 over 11, 3 over 11. Okay, this is called adjoint method. Now let's take a look at the second application. The second application is called Cramer's rule. So we are going to use the determinant to find the solution to a linear system. Let's take a look. Second application is called the Cramer's rule. So firstly, I'm going to give you the rule and give you the formula, okay? So if determinant of A is non-zero, okay, cannot be 0, then the unique solution to the linear system AX equals B is given by this one. Yes, x1, x2. Okay, if we have xk and k unknowns, then xk equals give this one, which is determinant of bk over determinant of A. Or we can just write down like a bk determinant of A. So here, what is bk? Let's take a look. bk is the matrix. Replace the k's column by b, the constant b on the right side is like k's column. I'm going to show you, okay, later, don't worry. And bk is the matrix obtained when the case column of A is replaced by B. For example, I'm going to show you like this one. If we have 1, 2, 3, 4, x1, x2, which equals 5, 6. This is ax equals b. Is that right? Okay. So what is bk means? So if let's see b1, the matrix b1 means we replace the first column by b. So what's b? 5, 6. And then we just keep other column the same thing. And let's take a look at what's b2. b2 means we replace the second column by b. So second column by b, so 5, 6 is the second column, and 1, 3 still the same thing. Something like that. Okay, now let's take a look at the example. I will show you how to use this rule to calculate the solution. We skip the proof. The proof is pretty long, okay? But the proof uses some calculus 3 method. It's like a determinant means the volume of a box. I don't know, do you still remember in calculus 4? Like calculus 3, you learn something like IJK, like cross product, U cross V and then dot other. So this means determinant kind of thing. It's kind of like an application of cross product and the dot product. Use Cramer's rule. We don't need to know the proof. We just need to know how to use the Cramer's rule to solve the linear system. So here the linear system is given by this one. 2x1 is a 3 by 3 matrix. That means A is given, B is given. We had this in our second midterm. In the first midterm, we used the Gauss-Jordan method, Gaussian elimination method. We reduce the augmented into row echelon and use back substitution, right? So here we're going to use the Cramer's rule, another method to find solution. Firstly, let's write down our matrix A. Matrix A means, so I didn't put the pound, that means the only coefficient matrix. Be careful. Coefficient matrix, like this one, right? And in the calculation, we have determinant. So let's calculate determinant. And the determinant for this one is actually 41. We skip this calculation. And let's take a look at what is B1. B1 equals to, replace the first column by B. What is B? 2, 5, 3. Look at this column. So B is this column, right? So replace the first column by B. And second column, and they're just the same thing. We just copy and calculate this determinant. This is 91. We skip the determinant calculation. We can use calculator here. Same thing for the homework, you can use calculator, and in the exam, I will just give you some easy ones, okay? So B2 will replace the second column by B. So B is 2, 5, 3. And just write down row 1, row 2 in A. And this determinant is 22. So you can try to write down B3. B3 equals to, replace the third column by B. And the first column, second column are the same thing. Okay, and this is -78. So let's see what is x1. x1 equals determinant of b1 over determinant of a. So b1 determinant is 91 divided by 41. And x2, 22 over 41. x3, negative 78 over 41. So what is the solution? Solution we like to write down this way, okay, in R3. So which is 91, 41. So you can see with this big number, it's impossible to solve by using Gaussian elimination, right? So this is the application of the other of the determinant. So now let's take a look at the exercise problem. You can use, calculator to find the determinant if you want. But let's just do 2 by 2. Okay, let's do 2 by 2. 0, negative 1, and times x1, x2 equals 1, 2. Let's solve this one. Okay, find the solution using the Cramer's rule. Let's take a look. And be careful, the determinant cannot be 0, right? If it's 0, definitely our solution, there's no solution because it's going to divide by 0 denominator. That's impossible. So we have to have determinant cannot be 0. Just be a little careful. And this determinant is negative 5. It's not 0. Okay. So firstly, I calculate the determinant, negative 5. And then I calculate B1. B1 replace the first column and calculate this determinant. Negative 1 minus 4, negative 5. B2, which is the second column replaced by B, which is 10. So what's the solution for this problem? The solution is pretty easy. So x1 is B1 determinant over A determinant, which is 1. B2 determinant divided by x2, divided by negative 5, so it should be negative 2. So this is x2. So this is the solution. Okay, this is Cramer's rule. So in this section, what we need to know, summary. 3 things. 1, calculation of determinant. Determinant. So we need to know how to calculate determinant of 3 by 3, 4 by 4 by simplify the determinant. Okay. Second, use the adjoint method for the inverse matrix. Adjoint A over A determinant. Adjoint is the transpose of the cofactor matrix. Number 3, find the solution by using Cramer's rule. Determinant of BK over determinant of A, and the BK is the matrix, replace the case column by constant B. So just need to know those 3 things. Okay, that's all about the determinant. We can stop here.